Hello, welcome everyone. Let's talk about cameras. In this, we will talk about cameras with lenses, depth of field, field of view, lens aberrations, digital sensors, and we will talk about two cameras. One is an industrial camera, the other one is a professional photography camera. So those days cameras used to be just a lens and the imaging sensor at the back. So it was a cavity which controls light entry only through the lens, and there was a cardboard or something covering the lens, and then the photographer momentarily opens this using the remote of the cardboard, and then an image is made, and he closes the lens after allowing some time based on the amount of light he needs to make the image on the lens. But now there are much faster versions available with all these things electronically controlled. Now, a homemade pinhole camera is something that Paul Debewick, this is a picture of that person, made using a DSLR camera. There he fixed a small cardboard here and made a little prick here so that light can come in and strike the CCD. So the images that you obtain look like this. For example, if the prick size is, for example, 2 millimeters, then the image look like this, not focused. 1 millimeter, focusing is higher. 0.6 millimeters, even higher. 0.35 millimeters, focusing is very good. Then the temptation is to make it even more small. Then less light gets through the prick, and also the diffraction effects take place. What that means is at the edges of this prick the light bends. That's diffraction. So therefore once again the blur takes place. So when you make this prick small enough, you can make the focused image, but the amount of light that you capture into the camera is less. So how do you get a lot of light into the camera? That is by using a lens. So the action of a lens is like this. Now you have a point in the scene, and then many rays of light emanate from that point, and what the lens does is focus them back to one single point. So one point in the scene, one point on the film. Now this is called thin lens model. Rays passing through the center are not deviated. It's called the pinhole camera model, and the pinhole camera model still holds in this case. So you can see all parallel rays in this case converge to one point on the plane located at the focal length. Now this one is called the focal length. Now other points project to a so-called circle of confusion. Okay, now let's take this plane. So one point corresponds to one point there on the film, so properly focused. And if you take another plane in the scene corresponding to this blue dot, there you go, the light focuses somewhere here, therefore there is a certain width for that one point represented on the film, and that's called the circle of confusion. Okay, so let's look at the thin lens formula, which most of us have done in high school. So here the parameters are like this. From the lens to the place where the parallel rays cut through the optical axis, this is the focal length, F. And then from lens to the imaging plane, the distance is d prime, and from lens to the actual object, the length is d. Yeah. Okay. Then we can consider the similar triangles. First of all, let's consider these two similar triangles, and then this height is the height of the object, that's y. This is the height of the object in the image height, actually it's y prime, and this distance as you can see is d prime, and this one is capital D. So therefore y prime divided by y is equal to d prime divided by d using similar triangles. Also there are two more similar triangles here. So this distance as you can see is d prime minus f, Therefore, once again, the corresponding distance to that is f. So y prime minus divided by y is d prime minus f divided by f. By removing y prime and y and rearranging terms, you get this formula. Any point satisfying this thin length equation is in focus. So 1 over d prime plus 1 over d is equal to 1 over f. So although theoretically there is only one plane in focus, you know that in practice there is a depth of field. So these are not in focus, these areas are not in focus, but this area is in focus. So shown in a different way in this image. So we can control the depth of field by using the aperture. So here you can see this is the opening of the in front of the camera lens iris. So here it's a large aperture. So large aperture means almost the whole lens is open. Therefore, if you take point 2 here, that one is in focus. Though, so circle of confusion is extremely small. But if you take point 1 there, light will focus here before this film, and therefore there is a circle of confusion there. And then if you take point 3, light will focus beyond the film, so therefore there is a circle of confusion there. So you can see only this plane is in focus, this plane is out of focus, this plane is out of focus. So how can you make the circle of confusion smaller? You can do that by making the aperture small. When you make the aperture small, so there is an aperture in front, so all the light that strikes the lens cannot pass through. So therefore you can see the circle of confusion becomes smaller if you observe the two diagrams. So changing the aperture size affects the depth of field. So small aperture increases the range in which the object is approximately in focus, but small apertures reduce amount of light, therefore needs to increase the exposure. That means the amount of time that you keep the shutter open must be exposed. So in broad daylight, if you want to make a image of a scene, a landscape or something, you use a small aperture size so that the full scene is in focus. Depth of focus is large, full scene is in focus. So for portraits and so on of people and so on, you use large apertures so that depth of field is small, only the face is in focus, the background is blurred. Yeah, so large aperture, small depth of focus, so you can see only this area is in focus. And small aperture, large depth of focus, the whole area is in focus, all the chairs. Yes. Then let's look at the concept of field of view. In degrees, what is the amount of scene captures vertically and horizontally? So you can see this is the CCD or the sensor or the CMOS inside the camera. So any point outside this green area does not emit light that strikes this CCD area. So maybe the light strikes here if you have the scene there. So there you can see the green area is the field of view. So how do you determine that? It's very easy. And so we can consider this as d. So therefore this distance is d by 2. So we can see that this angle phi is equal to tan inverse d by 2f. So therefore large focal length means smaller field of view, which we can see from here. So if you take like 17 millimeters, it's a very small focal length, and then you can see the field of view in this camera is, in this lens is 104. You can see a very large area here. When you keep on increasing the focal length, 28 area becomes smaller, field of view becomes smaller, 50 even smaller, 85 even smaller, and when you reach for example 1000, field of view is perhaps only this area. Yeah. Okay. So you can do things with this field of view. Now here in this example, here the focal length is large and the distance to the object is large. In this case the focal length is small and the distance to the image is also small. So in this situation you have the image, and here also you have the image. The car is approximately of the same size, but here the 3D nature of the car is disappeared, so it's like flattened, and here the 3D nature is present of the car. Yes. So large field of view, small f, camera close to the car, small field of view, large f, camera far from the car. So when you make portraits also, this effect is important. So here a lot of 3D nature in the picture. This is okay. This is too flat. So if you use a wide angle lens when you make portrait pictures, your faces will become weird, so you should not do that. So telephoto makes faces flat, so you have to pick a standard focal length for those. So sometimes you have lenses with a fixed focus for making portrait pictures. So there are cameras called orthographic cameras. That means the rays are parallel. These are actually theoretical cameras. But when you have an actual camera, it's the imaging model is perspective. What that means is the parallel lines in the scene. All these lines are parallel in the scene, right? They are no longer parallel in the image. But if you approximate to keep these lines parallel in the image also, that imaging situation is called weak perspective. So that you do by increasing the focal length and increasing the distance of the camera. So there are the effects like the Dolly Zoom. I invite you to look at these things using your free time, and then Dolly Zoom, called the vertigo shot and so on. Yeah. So now we looked at the depth of field and field of view. Now let's look at lens aberrations briefly. So these lenses have, if you take a lens, there are many lenses inside. I think these lenses are made with taking a lot of time to make the lens perfect by slowly cooling the glass. Yes. So one effect is the one lens flaw is called vignetting. So it is a term used in photography and optics to describe the reduction in brightness or saturation at the edges. You can see especially at the corners compared to the center. This effect is caused by various factors such as the physical design of a lens, improper use of filters in lens or hoods. If you use hoods also this can happen, or other environmental factors such as poor lighting conditions and so on. So then next effect is lens radial distortions. So these are caused by imperfect lenses. Deviations are mostly noticeable near the edges of the lens. So you can see there are two types: pincushion distortion and barrel distortion. So whatever grid that is perpendicular to each other, straight lines grid in the scene appear like a pincushion in the pincushion distortion, and like a barrel in the barrel distortion. So radial distortion is usually more pronounced towards the edges of the image and can be caused by various factors, including the lens design, the aperture setting, and distance between the lens and the object. So usually if the camera is far from the object, these effects do not take place. But these things can be corrected by the camera design or in software. So another flaw is the spherical aberration. So, radial distortion and spherical aberration are both types of optical aberrations. They both affect the quality of the image, and in machine vision, you have to correct these before you use them for other tasks like camera calibration or measurements. Spherical aberration, particularly, is caused by the way that light rays pass through the lens, and that is not perfectly shaped or aligned. It causes the edges of the image to be less sharp or focused than the center, resulting in a blurred or hazy appearance. Spherical aberration affects the entire image rather than just the edges, and it can be caused by factors such as lens shape, lens alignment, and the refractive indices of the material of the lens. Yeah. So then another one is chromatic aberration. I think you may have seen this near the outage. You can see a rainbow-like effect. That happens because different wavelengths of light have different refractive indices. So it is results in color fringing like rainbow effect at the edges. So special lens coatings are the things that we can do to remove chromatic aberration. So now we have looked at lens aberrations also. So we now briefly look at digital sensors. Now if you take a camera and there is a digital sensor, they used to be CCDs, now most of them are CMOS sensors. So it's actually a photon to electron conversion. The light strikes these cells, and one of these cells is called a pixel, and then they are converted to electrons or current. So if we briefly look at an industrial camera example, this is a Basler camera, a famous industrial camera manufacturer. The sensor vendor is Sony. Sensor type is this. It has global shutter. So global shutter, in contrast to rolling shutter, means these are two different ways that cameras capture light by opening the shutter. Global shutter, also known as the electronic shutter, captures the entire image sensor simultaneously. In a global shutter camera, all the pixels of the sensor are exposed at the same time, and the exposure time is synchronized across the entire sensor. The image is then read out and digitized in one operation. So global shutter is commonly used in industrial cameras where timing, precise timing, and fast speeds are required. But in photography cameras, it's usually the rolling shutter where one line of pixels is captured once, and then other lines are captured sequentially. So as a result, the image is captured over a period of time, as you can understand, rather than all at once. So this can cause distortions, especially when there are moving objects. Because when the object, now you capture one line, when you capture other last lines, the object has moved by a certain amount. Um, so yeah, so you can see the difference. So this is global shutter. So since the format is 1 over 1.8 inches, what that means is if you take the CMOS sensor, it measures diagonally this amount, 1 over 1.8 inches. So that means about yeah, I should have written inches here. That is about half an inch, right? So therefore you can calculate the sensor size because this ratio 4 to 3. Sensor size in this case is 6.7 millimeters to 5.6 millimeters. So if you take each of those elements that we discussed in the previous slide, this is called a pixel. We write it as px, 2.74 micrometers times 2.74 micrometers for this particular example. Frame rate is at 23 frames per second. It's a color sensor. And then a pixel bit depth 8, 10 or 12. What that means is each of these pixels can be represented using an 8-bit number, 10-bit number, or a 12-bit number. And the connectivity is gigabit Ethernet. That means you can connect an Ethernet cable to the camera. That's how you capture the images or the videos. And that must be PoE, power over Ethernet. What that means is power to the camera is supplied by this cable. The switch must be able to provide power over Ethernet. So those are usually marked in yellow lines, these ports. Otherwise, you can use a PoE injector. So synchronization means that at the time at which the images are taken can be free-run, hardware triggered or software triggered. Then there is exposure control. As you know, the exposure is a fundamental aspect of photography, and it is about the process of controlling the amount of light that reaches the camera's imaging sensor. So, as you know, proper exposure is essential to make a good image. So there are three key parameters, as you know, for exposure control. That's aperture, we looked at that, and shutter speed, we did not look at that too much, and then the ISO. So aperture is the size, as we saw in one of the previous slides, so that during the time that the shutter is open, shutter is open, a large amount of light is taken in if the aperture is large, and so on. So by the aperture, we can control how much light reaches a sensor. So a large aperture is signified by a small f number. So will allow more light to pass through, while a small aperture, a large f number, will allow less light to pass through. So shutter speed is measured in a fraction of a second. Refers to the amount of time that the camera shutter remains open to allow light to reach the sensor. So by adjusting the shutter speed, we can control the duration of exposure. A fast shutter speed will allow less light to reach the sensor, while a slower shutter speed will allow more light to reach the sensor. And then the third parameter is ISO. ISO refers to the sensitivity of the camera imaging sensor to light. And you can adjust that. By adjusting ISO, you can control how much the sensor amplifies the light that reaches it. So therefore, if you have small aperture and fast shutter speed, then enough light is not coming to the sensor, so you can adjust the ISO to a large value. Or if you are taking nighttime images and you do not want a blur, then you can increase the aperture, so, increase the ISO size. Yeah, so those three parameters are the ones that control this. So exposure control is how you control them in the camera. Yeah. Okay, then if you take a professional photography camera like Z7, it's a mirrorless camera. It's not a DSLR camera. It's a mirrorless. That means there's no mirror. So it's electronic shutter in this case. It's I think mid-range camera. So it has 4.7 million pixels compared to the 5 million pixels that you had in this case. And shutter is electronically controlled and so on. Then shutter speed, so 108,000 or 1 to 30 seconds. So 108,000 may be extremely fast sports, that kind of photography. 30 seconds maybe if you want to make images of stars and so on, then you use this. Then sensor format is FX format. So FX and DX are two different sensor formats that Nikon uses. So FX is actually full frame. So it measures 36 millimeters times 24. So this is 24 millimeters height is the height of a regular film. Those days there were film cameras. So that's why it's called full frame. So therefore it's large and the individual pixels are large. So therefore these sensors are less noisy and therefore they are used in more professional cameras. So DX on the other hand is smaller sensor format. It's 24 to 16 millimeters. So 16 is the height. They are in usually more affordable cameras. So this is slightly expensive. So therefore it's FX format. Once again, this is CMOS. Sensor size is you can see large. So it has been rumored. It's not official information that the sensor is this one from Sony. And you can see, as we talked in the previous slide before, ISO can be controlled from 64 to 25,000. It's usually large number. And then the movie resolutions, total pixels, and so on. Yeah. So anyways, if you take a sensor, so it is a grid of one single plane, so it does not capture all three colors. So for example, if this one is supposed to capture blue, this will capture green and so on. So we can see as there are twice as many green pixels than blue pixels and red pixels individually. So this is done using a filter. So you can see there is a filter on top of the sensor, and then you have this resulting pattern. So that's how you capture three different colors. So therefore now, for example, if you take this pixel, there is no green on that. If you take this pixel, there is no red or blue on that. So therefore, using nearby pixel values, you have to approximate those colors. So this one is called the Bayer grid. So estimating these colors is called demosaicing. So why more green? It's because the human eye is more sensitive to green wavelengths. Yeah. So this demosaicing process by which digital cameras convert the raw pixel uh, values to compute the colors. Uh, it results in some artifacts also. Uh, so because you yes, yeah, I can show that using this one. It's called Moire pattern. So then when there are these alternating colors like that, like this palm branch, specifically like this in this case, so you can see there's a confusion, and then of color estimation of some pixels, and then wrong colors will result because of that. Um, so these are commonly seen in these branches, fabrics, other patterns that have fine structures. Um, so sometimes in buildings and other structures which are far away from the camera. So so repetitive fine details, repetitive fine details. So yeah, anti-aliasing, that kind of things have to be done to remove this or reduce this. So digital camera artifacts are there miscellaneous ones like noise, Low light is where you notice noise most, and light sensitive ISO noise trade-off, and there are things called stuck pixels. And in camera processing, over sharpening can produce halos like this, and then when you compress JPG, artifacts are there, and then blooming, color artifacts and so on are there. So you are most welcome to read about those. So some historical milestones have also been there. So pinhole model have been known by 407 to 390 BC, and even by Aristotle, and then camera obscura by Leonardo da Vinci in 1631, and then first photo Joseph, I don't know how to pronounce his name now, 1822. Then first photography film Eastman, then first consumer camera by Sony 1981, first fully digital camera by Kodak, and so on. So this is supposed to be the first digital scan photograph, and so on. So number of cameras have been skyrocketing. So these are all smartphone cameras, and the mirrorless cameras are also coming into the picture. DSLR cameras are small, compact digital cameras are the many, and then actually this there's an explosion of phone cameras. Okay, thank you.